it off to the first tutor.
All right. Hey, everyone. So we're going to start off today's session by talking about the probabilistic definition, specifically when you can use it. So in class, you went through how to derive the probabilistic definition from the statistical definition shown here. I'm not going to go through the derivation right now. You can go look through your slides for that. But I definitely recommend becoming comfortable with that derivation and knowing specific parts of that, because you may be asked to derive that on a test, or we've definitely had problems where they've given you a similar sort of derivation on a test. So be comfortable with that. But important thing to note here is that we use Stirling's approximation to get from this to this form. And the question becomes, are these two forms equal to each other? And our first thought is, yeah, probably. We were able to derive one from the other. But we find in some cases they are equal to each other, and in other cases they aren't. So let's start when they are equal to each other, is when we look at this from a system perspective. So remember, system is, I like to think of it as your state. State is a general description of what's happening in your system. So for this problem here, this is taken from your slides, you have 3 molecules and you have 3 units of energy. You can then split up those 3 units of energy any way you want. You can put 1 in each molecule, you can put all 3 in one molecule, or you can mix and match like here. And if we plug into both equations, we find that these two equations equal each other, because we get 10 different microstates and they're equally as likely, because we're saying we can distribute our energy just as easily for this set of microstates as for this one. And they're equal. I like to think about this system perspective or state perspective as sort of like independence in probability, like your coin flips. Each coin flip you do is an independent event, the same way each microstate here has an equal probability. It's another way you can think about it is drawing from a bag of marbles with replacements. So if you draw out one marble, the next time you draw, you're going to replace it again. So you're always drawing with the same amount and same type of marbles. The probability doesn't change. So this becomes interesting, though, when you zoom in a bit and look at it from a molecular perspective. Now we're going to say, all right, so we have this system with 3 molecules and 3 units of energy. What's the probability of finding a specific molecule at a specific energy level? And that's what we showed here. What's the probability of finding it at the 0 energy level, first, second, third? We're just looking at our microstates for that. But when we plug into both equations, we find that they're not equal to each other. And as Professor Grove said, doing this math with the probabilistic definition is not accurate. So why is that? Let's do something called correlation. I think the term correlation can be a little confusing. You can think of it as dependence in probability, where if you select one condition or set a choice for something, it influences the future choices you make. So in this problem, if you say this molecule here has an energy level of 3, you put all 3 energy units into that molecule. That means the other 2 molecules have to be at the 0 energy level, right? There's a 100% probability you'll find them there. But the math you did previously kind of assumes that you still have those equal probability, not equal probabilities, but different probabilities. So that's like drawing from a bag of marbles without replacement. If we have these 10 marbles and we're looking for green marbles, let's say, we draw 1 green marble out. Now, next time we ask, what's the probability of drawing a green marble? Our probability becomes 3 green marbles out of 9 because we're not replacing. And you can see the probability decreases. So, but as we find out, we need to look at Stirling's approximation. That's important because when we derive the probabilistic definition, we said Stirling's approximation is only valid when we have large values of n. In our case, it's large values of molecules. And we find as you increase the number of molecules, this probabilistic definition becomes more and more accurate. Let's go back to our bag problem here. Imagine, so we first did this for 10 marbles total. Imagine now, instead of 10, we have 1,000 marbles, and we kept the proportions of the colors here the same. So we start out with 400 green marbles out of a total 1,000, and we still have our 0.4 probability, like before. Now let's say you draw 1 green marble out, and you ask, all right, what's the probability of drawing another green marble? Now you have 399 green marbles over a total or remaining 999 total marbles. And we find that probability is equal to 0.399399 repeat. You see the probability still decreased, but not by as much, right? This number is a lot closer to our original probability of 0.4. And that's why Stirling's approximation is important, because at large number of molecules, this decrease in consecutive probabilities decreases. It becomes basically the same. So imagine doing this drawing with, instead of 1,000, 1,000,000 marbles, 2,000,000. Imagine doing it with 6.02 times 10 to the 23rd molecules in general. You can imagine with each time you draw out of that bag, the probability doesn't change as much. And that's essentially what we're saying here. With large values of molecules, your correlation decreases such that it more or less becomes irrelevant. And we can say, all right, this math we did previously that we showed on that previous slide, we can say these probabilities are accurate. So when we plug in, we can say this is an accurate representation of entropy in the system. So just to summarize, I went through that really fast. To summarize, so you can use your statistical definition when you have small numbers of molecules or when all the microstates you have are equally likely. So you can think of using your statistical one if you have a situation like flipping multiple coins. They're all independent events. They're all equally likely. You can use your probabilistic definition when you have no correlation or dependence, or when you have large numbers of molecules. I remember from when I took the class, I think we defined that as like greater than 100 molecules. I would talk to your GSIs and talk to the professors just to confirm that, because I'm not sure if that's completely correct. But basic idea is with large number of molecules, your correlation decreases such that you don't need to account for it. And coming back to this idea, when all microstates are equally likely, that's the system perspective, right? And you can use the statistical definition, but you can also use your probabilistic definition, but only if you say that the number of molecules, but in this case, the number of things you're looking at is equal to 1, because you're looking at one system. In that case, you can just simplify this equation to this and use your probabilistic definition. So that's actually all I had so far. Does anyone have any questions? This 2-3 minutes. Okay, well, feel free to message me in the chat, and I'll do my best to answer it there. But the next tutor can go ahead, get started.
Okay, so today I'm hoping to give you a little bit of a recap on what was discussed in Monday and Wednesday's lecture. So this is going to be a little bit about the ideal polymer equation and also random walk. But before we dive into this, I just want to give a quick intro on partial derivatives, because I think these show up quite a bit in this part of the course, and they're very similar to single variable derivatives, but they can just be a little bit confusing. So first, let's consider a multivariable function like the one that you have here. So in single variable calculus, you're used to seeing functions like y equals f of x. And so in those cases, when you wanted to ask, how does y change in relation to x, then you would kind of just take the slope at any given point on the graph. But when you have some function like z is equal to f of x and y, then it's kind of hard to say, how does z change, because there are actually different variables that influence it. So for example, you can't really take the slope at a particular point because there are two variables that are influencing it. And so this is where the notion of a partial derivative comes into play, because what we can do is we can essentially freeze every other variable except one, and then just see how changing that one variable will influence z. And I think box 8.3 in your book does a good job of showing this. But if we were to take the same graph or the same surface from here and take a partial derivative first with respect to y, what this means is we look at this function z equals f of x of y, and we just ask ourselves, if we hold x constant, basically you freeze the value of x and you move y very slightly, what is going to be the overall change in the function? What is the overall change in z? And in this case, you'll see that it's a flat line, meaning that if you change y a little bit at this point, there won't be much of a difference. On the other hand, if you hold y constant and you move x very slightly, you can see that you would get pretty big changes in z based on the way you move. And so you can generalize this to functions that have many more variables, more than just like x and y. And so we can bring that into the next point about partial derivatives, which is like this law of total derivative. And so in this case, what this kind of equation here is just telling us is that if you have a function that is composed of two variables like x and y, and you want to know what is like the total change in that function, you would first have to assess the change that one variable is responsible for, and then multiply it by a small change in that variable. So this quantity is like saying f changes by this fraction when you move x by a small amount, and then you multiply by that small amount x to get that total change, and you do the same for y. So both of these two terms represent like the total change in z with respect to x multiplied by a small increment in x, and then the same thing but a small increment in y, and that gives you the total derivative. And so next, we can apply this to some of the thermodynamic equations that you've seen in lecture. So first, I'm just going to point this out that this was like shown in lecture, but this is just a useful quantity to know, which is that temperature can be expressed as the partial derivative of energy, U, with respect to entropy. And just one quick thing I want to point out here is that kind of as the subscript, we have N and V. And this just indicates that while we're taking this derivative, we've kind of held these variables constant, or we've basically like frozen every other variable so that we can only see what the change in U is with respect to S. And in many cases, when you're taking partial derivatives, it can also just make sense to ignore certain variables if you know, for instance, that your energy function is not going to be influenced by temperature if everything's happening at the same temperature, or if the total number of particles in the system isn't changing, then you know that you can ignore something like n. And then this is just a recap of some equations relating to the total energy of a system. So this is from the first law of thermodynamics, which says that the total energy change in a system is given by the change in heat flow, and then also the work done to the system or the work done by the system. And for a lot of this class so far, you've looked at the example of a gas cylinder or gas expanding against a cylinder. And in those cases, you can just replace dq with the thermodynamic definition of entropy, which is that S is equal to Q reversible divided by T. And so you just replace Q with T times S. And also, because if we're considering the case in which we have gas expansion type of work, the type of work will be PV work, which is why we write this. And so, like I was saying previously, if there are some cases in which you assume that your energy is really only influenced by, say, entropy and volume, then you can write out the total change in energy as the partial derivative with respect to these two things. So if we're assuming that it's really only entropy and volume that are influencing energy in this case, then we can just take the derivative, partial derivative with respect to these two things, hold the other variables constant, and multiply by small increments in ds. So I don't think you'll be asked to recreate whole proofs at this level, but I'm just explaining this so that when you do read a proof, it hopefully makes a little bit more sense. So next, I'll go over the protein stretching example that was discussed in class. So here, what we have going on is we have some protein. And what's happening is that this instrument is kind of stretching the protein kind of longer and longer. And while this is occurring, we're measuring the force, or essentially the tension in the protein. And just the key things to notice here are that the green region corresponds to the protein going from a really jumbled and clumped up thing to something that is a little bit more straightened out. And then here, what happens is you have a sudden drop in the amount of force that's required because there can be some type of secondary structural element, maybe like a lot of alpha helices or maybe a beta barrel, that after having enough force or tension in the protein, it just overwhelms the intermolecular forces. And so then all the protein that was clumped up in some type of neat arrangement now becomes straightened out. And so this kind of introduces a lot of slack, and then that reduces the tension, but then this increases as you increase the length of the protein. And so our goal in discussing an example like this is really to come up with some way of describing the system using the thermodynamics that we know, and also some math to come up with something that's generalizable to something more than just pulling a protein. And to give you some intuition to get us started on this, what we know in this example that's different from other examples is, well, first of all, if we're just stretching a protein, the temperature we're not really expecting to change, and we can probably hold that constant. And also when it comes to the work that's being done here, there isn't any gas that's expanding against the cylinder. So the work is not going to be PV work like we've seen before. So really the work comes in the form of this force times the displacement length, because as you'll recall, the definition of work is force times distance, or that's one of the ways to define work. So that's the work in this case. And if you want to think about the energy trade-off that's happening, we're doing work to the protein by stretching it out, because there is like a resisting force as you're stretching the protein. But in exchange for that, we're reducing the entropy of the protein, because as it goes from something that's really tangled up to something that's more straight, like a very tense, I guess, segment of string, then it's reducing in entropy. And so we can kind of think about all these things in the form of an equation. So if you'll recall from 2 slides ago, I had the total change in internal energy, but that was a function of both the change in entropy, the change in internal energy with respect to entropy, and also the change in the internal energy with respect to the volume. But in this case, because there's no pressure volume work, we can just use length. And this is, again, first law of thermodynamics. And now this is just rewritten so the dW term is more explicitly F times dL. And this is just a diagram that explains, once again, what we're doing. If we have some protein like this, we're trying to increase its length. And as we're doing so, we're encountering some type of force. And so, again, yeah, the main differences here is that you have the F dot dL, and that's why you take the partial derivative with respect to length. And one thing we can do to kind of simplify this going forward is we make a pretty big assumption. And this assumption is that all configurations of this protein chain at whatever length are equivalent in energy. So this is like saying when the protein is really clumped up in almost maybe like a sphere, like a ball of yarn, and when the protein is all the way stretched out like a perfect piece of string, all of those configurations have the same energy. And so, of course, from what you know about proteins, that probably doesn't really track with reality very well, because you know that there are lots of intermolecular forces. And so at this point, we're kind of assuming that there is some type of ideal behavior. And this is kind of where we make the pivot to assuming that this is more like an ideal polymer. And kind of what you saw in lecture is that the rest of this derivation talks about coming up with an equation to model the ideal polymer state, or the equation for the ideal polymer state. So this is a pretty big assumption. But this allows us to simplify things, because if we now take the partial derivative of this with respect to length, we know that the whole thing should eventually equal 0. And so what that looks like mathematically is you just multiply by d over dl to everything on this side, and you end up with this, and you get this. So if we think about if this makes sense for a moment, consider that as we're increasing length, we would expect the entropy to decrease, right? Because the protein's becoming more straightened out. And so this derivative term should be negative, meaning that your force is positive, which is what we would expect. We would expect to encounter some resistance as we're stretching the protein. And in the next slide, I'm going to talk about how this dsdl term is quantified. So first, stepping back, we can think about the definition of entropy. So this is the statistical definition of entropy. And so far in this course, you've seen many different definitions of entropy. But the statistical definition of entropy is always true. It just happens to be the case that sometimes if you're working on a problem that has trillions of molecules or 1 mole of particles, calculating the multiplicity can be really, really complicated and almost impossible for current calculators. So that's when you use different definitions. But entropy can always be expressed as kb times the log of the number of microstates. And so for our example, we can assume a few things. So let's suppose that we have some quantity W star. And let's say W star represents every single possible microstate that our protein chain can take. So at any given length, every single possible microstate. And then let's also assume that we have some function P of L, which tells us the percentage or the fraction of the microstates in which the chain is at length L. So then the entropy when the chain is at length L would just be given by this. And as I will go over later from the random walk derivation, the proportion or fraction of microstates in which the chain is of length L is really given by a Gaussian distribution, or also known as a normal distribution that's centered at 0 with this variance. But once we have this, we can take the partial derivative of this with respect to L. And of course, you're not really expected to go through this again, but this is just for you to understand. And we can finally come up with this relationship here. And if we'll notice, this now allows us to express force in terms of N, which is the number of monomers in a polymer, as well as L, which is the total length of the polymer chain, and lowercase l, which is the length of an individual monomer. So this really ties everything together, and this is the ideal polymer equation of state that you derived. And then later in lecture, there was also another slide for a worm-like chain model, which is just a slightly better approximation than this that makes a few additional assumptions. So before I proceed, are there any questions so far? Okay, and so the next thing I want to talk about today is the idea of Gaussians and random walk. And so to kind of start the discussion about what a random walk is, so first of all, well, in order to build up to a random walk in 3 dimensions, we can start with something that happens only at the 1-dimensional level, which is just moving along the x-axis. So consider this experiment where you start at the origin and then you basically flip a coin to determine whether you should move left or right by some constant distance. And if you repeat this many, many times, you end up with a distribution that looks something like this. So if you do 100 steps, and then you repeat that 100-step experiment maybe thousands of times, you will get a distribution like this, where this position here tells you how far away from the origin that you got. And notice that this looks like a normal distribution, right? A Gaussian distribution that's centered at 0. And if you compute the variance of this, or which is the standard deviation squared, you will get something like L times the square root of n. So just by moving completely randomly, this is the type of behavior that you get. And we can, of course, generalize this to 2 and 3 dimensions. And so if you consider the 2-dimensional case, this is what a Gaussian distribution looks like when you have an x and a y variable. And the way that you can read something like this is you can consider, okay, like let's say I have some xy coordinate, and let's say it corresponds to this point on the surface, then the probability of you seeing that xy coordinate would just be the value of this cone object at this surface, at this point on the surface. So really quickly, does anyone want to tell me which color band on this multivariate Gaussian corresponds to the highest probability? You can just unmute and answer. All right, so I think in the interest of time, I'll just like go ahead and get to the answer. But one way to tell which part of this Gaussian corresponds to the highest probability is if you can just read the axes here. So the tallest thing here would be this red region, but you can also think about it intuitively in the sense that if you have a 1-dimensional Gaussian distribution, the most likely or most probable value will be the thing that's right at the center at the mean. And so whatever's kind of at the top of this traffic cone or mound, that is going to be the thing with the highest probability. And so this is what a Gaussian looks like in 2 dimensions. And then for 3 dimensions, we can't really plot something like that. So you just have to imagine that a lot of these kind of rules still hold. And so for the next part of random walk, let's consider a vector with 3 components, x, y, and z. And so this can be a gas particle that has velocity components x, y, and z. And one assumption that we can make is that all 3 of these components are independent, meaning that your x velocity does not influence your y velocity, and that shouldn't influence your z velocity. Then the probability of seeing these 3 would just be their product. But what you know about working with probabilities is that if you multiply 3 numbers that are less than 1, and probabilities are all less than or equal to 1, if you multiply 3 numbers like this together, you're going to get a very small probability. And most of the time when we're looking at gases, we're not really interested in knowing how many gas particles have a positive x and a negative y and a neutral z or something like that. We kind of just want to know how many gas particles are between this speed and this speed. And for that, we can consider all the points that have a certain magnitude or the ones that have a certain speed. So if you square all the individual components, you will get r squared, which is the speed squared. And if you think about what this equation represents, this is actually the surface of a sphere. So this is like the set of all x, y, and z points that lie on the surface of a sphere with radius r. And so now what we can do is, if you want to count up the probability of a gas having this speed, we will just take the individual probability of seeing a point with x, y, and z velocities, and also the fact that there are a bunch of points distributed on a sphere. And so loosely, the approximation that you can make is you can take the surface of the sphere and you can multiply it times these joint probabilities. And since these probabilities all have a Gaussian distribution, every single probability is basically the same, like it comes from identical distributions. That's why you can just use the x cubed. So this is like the Gaussian cubed. And you did something very similar to this in lecture, except you were considering the two-dimensional case in which you're only looking at x squared plus y squared. And in that case, instead of getting the surface of a sphere, you got the perimeter of a circle. So since we're moving to one higher dimension, you just generalize one dimension more. And just the last comment I want to make is that this is pretty similar to a chi-square distribution with k equals 3. And that's actually where the Maxwell-Boltzmann distribution comes from. It's very similar to a chi-square distribution in which you have 3 degrees of freedom. And so here I just have the two distributions so you can observe the kind of similarity. So this is the Maxwell-Boltzmann distribution for speed, and this is a chi-square distribution with different values of k. Again, you won't really need to know like how to derive the Maxwell-Boltzmann distribution or anything like that, but this is just so you have some idea of where this distribution comes from. And hopefully this helps you a little bit with some of the intuition behind, I think, the last problem in the homework set, in the problem set. So yeah, that's all I have. Does anyone have any questions? Okay, so I'll stop sharing and I'll move on and let the next tutor begin. You can also just message any questions you have to me in the chat.
All right. Hello, guys. So today I'm going to be going over the Boltzmann distribution, and I'm going to be tying it to what we've learned so far about multiplicity and entropy. So this is a molecular energy distribution, and you guys have probably seen this before. And first of all, I just wanted to go over what an energy distribution exactly is. So let's say you have a large number of molecules, for example, 10,000. So most of the time, it's not like all 10,000 of these molecules are going to be at the same energy, right? Some of them are going to have higher energy, some of them have lower energy, and that's kind of just basically what an energy distribution graph is trying to tell you. So there will usually be some kind of energy distribution. Like, for example, 5,000 molecules could be at the lowest energy level, and then the other 5,000 could be at the next highest energy level. Or maybe you could even have 7,000 at the lowest energy level, 2,000 at the second highest, and then 1,000 at the third highest. But basically, how the energy is distributed in a system matters when it comes to entropy, because the entropy increases as the number of energy levels that are occupied increases. So the way I like to think about this is that molecules like us want to socially distance, or I mean, we don't want to socially distance, but right now we have to. So yeah, they like to be as splayed out as possible. So I kind of like to think about this like rows of seats in a movie theater. If you have 3 rows of seats, it's much more ideal to have 15 people spread out over those 3 rows rather than have them all in one row. So here, if you think about each box as a seat and each X as a person sitting in that seat, this is kind of dumb. Like, this would never happen, right? 15 people crowding into a theater would not all sit in the first row, especially if there's a second and a third row empty. So it's much better to have a distribution among the 3 rows rather than have them all in one row. So this is better. Now there's 10 people in the first row, 3 people in the second row, and 2 people in the third row. And this is better because there's people in each row, but the most ideal situation is to have 5 people in each row. And so I kind of think about molecules being the same way. They want to be as spread out and far away from other molecules as possible. So another helpful analogy for understanding energy distributions of molecules is to think about picking dice from a pile and recording what number from 1 to 6 you get. So if you consider this for scenario A, you just have blue dice, and blue dice in this case are all unbiased dice. meaning that the probability for each outcome from 1 to 6 is 1/6. So in the second scenario, B, you now throw in some biased die. So the red die are biased towards the outcome 2, while the green die are biased towards the outcome 4. So you basically end up getting a higher probability for 2 and 4, while you get a lower probability for the rest of the outcomes. And then for scenario C, now you only have biased die that are all biased towards the outcome 3. And so the probability of getting 3 is now basically 1. It's not exactly 1, but it's basically 1 because all of the other outcomes are very negligible. So, and this is also reflected if you do the math for the entropy per molecule. So if you get S over NKB, so S over NKB is basically an entropy measure. It's actually the entropy per molecule expressed as a multiple of Boltzmann's constant. And this calculation is useful when you're comparing entropy between situations where the number of your molecules stays constant. So you're kind of just dealing with numbers that are more workable and easier to think about rather than like a really small number, which is what you would get if you multiplied by Boltzmann's constant. But anyway, if you calculate these terms, you would get 1.8 for scenario A, 1.64 for scenario B, and 0 for scenario C. So basically, the entropy of a system increases as the probability of alternative outcomes becomes more even. Okay, so for practice, let's say we have 10,000 molecules. And in A, half of the molecules are in the lowest energy level and the other half are in the next level. And in B, the molecules are evenly distributed over the first 5 levels. So do you think A or B has higher entropy? So if anyone wants to say what they think, please unmute yourself or write it in the chat. It's okay. So we're getting B. Yeah, so B has higher entropy because, right, as I said before, the entropy increases as the number of energy levels that are occupied increases. So, okay, so far we've been comparing systems that have different energies, but now we're just going to talk about systems with a fixed total energy. So for a system with a fixed total energy and a fixed number of atoms, there are multiple energy distributions associated with it. And these are some examples of energy distributions for a system with a total energy of 27 and a total number of 30 molecules. And obviously, these are just 2 examples of energy distributions, but of course there are many more distributions. And then each energy distribution corresponds to many different microstates, right? So these are just examples of different microstates for each distribution, but also, again, keep in mind that these are only examples and there are way more than this. But the takeaway point is that the energy distribution with the highest multiplicity or the largest number of microstates is the Boltzmann distribution. So as a system relaxes to equilibrium, its energy distribution tends toward the Boltzmann distribution. So in other words, it tends towards a state of maximum multiplicity or maximum entropy. And when you're dealing with, especially when you're dealing with a large number of molecules, like on the order of 10 or even 20, non-Boltzmann distributions are highly unlikely. So basically what that means is that if you have a system with many molecules at equilibrium, the energy distribution that its molecules will have is, it's much more likely to be the Boltzmann distribution rather than a non-Boltzmann distribution. And because it's so much more likely, we just say that it has the Boltzmann distribution. So this is represented by an equation, as you see here, and notice that it's an exponential function, which you can see right here in this graph that it looks like an exponential graph. And then P sub j is the probability of finding a molecule in the J energy level. U sub j is the energy of the energy level, and A is a constant. Okay, so obviously, since P is the probability of finding a molecule in a given energy level, hopefully it makes sense that if we take the sum of all of the probabilities of each energy level, it should equal 1. And the constant A is basically what takes this into account. So I'll show you that here. So this, if you start with this, which is what we just said, where the sum of all of the probabilities equals 1, and you substitute this Boltzmann equation for P, you get this equation. And basically, if you isolate A, you get 1 over this expression here. And this expression here has its own name. It's called the partition function, or Q. And basically, the partition function indicates the accessibility of higher energy levels of the system. So the higher Q is, the more molecules occupy higher energy levels. So this is kind of like, I realize that's kind of an abstract idea, but I think it'll be clearer once you use it in an example. So let's say we have two systems again. So system A has, hopefully you can see that it has a greater percentage of its molecules in the higher energy levels than system B. And yeah, what do I mean by higher energy levels? So like that's arbitrary which energy levels you look at, but let's just say, let's just look at the energy levels above 2 kBt. So everything from 2 kBt down, let's just ignore and call that our lower energy levels. But our higher energy levels, you can see that system A has a 0.012 plus 0.032 probability of finding a molecule there, whereas molecule B has only a 0.016 probability of finding a molecule there. So system A has a larger fractional occupancy in the higher energy levels than system B. And this is reflected in the partition function or partition coefficients. If you do the math using the equation from the previous slide and find the value of Q for each of the systems, you find that Q sub A is 1.571, Q sub B is 1.153. And so QA is greater than QB. And that makes sense because as we saw, a higher Q means that the system has more molecules in higher energy levels. Yeah, so that's the end of my slides. The next tutor can present, but if any of you guys have questions, please message me in the chat. All right, I'll stop sharing.
All right, so for the last presentation of today, I'll be going over Gibbs free energy. And it's a pretty nice concept because it brings together everything you guys have learned about entropy, energy, temperature. And it's a pretty useful parameter when deciding when a reaction will be favorable or not. So let's get started. So yeah, to understand Gibbs free energy, we have to revisit entropy. So as you guys all know, there's a statistical definition, which is simply counting a number of microstates. And then there's also the thermodynamic definition, which takes into account heat and temperature. And so to be able to understand Gibbs free energy, we have to connect entropy to energy. And to do that, we need to understand temperature. And temperature is essentially the property of the system that becomes equal on both sides of a thermal contact at equilibrium. So for example, in this case here, you have a system A and a system B, and at equilibrium, the temperature on both sides will be equal. At the same time, at equilibrium, the total entropy of the system must be maximal. In other words, the change in entropy has to be zero. So now that we want to rewrite entropy, how can we rewrite it in terms of energy? So this kind of goes back to what Pujan was talking about partial derivatives. We can use the statistical definition of entropy and rewrite it in terms of volume, energy, and the number of molecules. And to do this, we use partial derivatives. Again, you don't have to rewrite this in class, rederive this in class, but it makes sense because in the first part, you're setting energy, number of molecules constant, and you're calculating entropy in terms of changing volume. In the second one, you're changing energy, and in the third one, you're changing the number of molecules. But to make this a bit easier, we're going to assume the volume and number of molecules is constant. So we can essentially just cross these two off because this will be 0 and this will be 0. So the change in entropy will be the partial derivative with respect to energy. And then, as we talked about last week, entropy is additive. So if we have system A and B on both sides of the thermal equilibrium, we can write the total change in entropy is simply the change in entropy of A and the change in entropy of B. So this is our first equation. And then at the same time, we know that at equilibrium, the total change in energy is also constant. So if you rewrite du A plus B is 0 equals du of A and plus du of B, we can rewrite that total change of energy of system A is equal to the negative change of the system B. And if you notice in the first equation here, we also have dua and dub. So if we rewrite these two equations with each other, we get the simplified equation of that the partial derivative of A, keeping volume A and the number of molecules A constant, equals the partial derivative of the change of entropy with respect to energy, keeping the number of molecules B and the volume B equal. So why do we do this? Well, in the very first slide, I said that temperature is the property that's equal on both sides at equilibrium. And in this case, we're saying that these two properties are also equal. So it makes sense to write T equals this and this. But if you notice at equilibrium, this is not the only thing that's constant. Another property that's constant is the partial derivative of u with respect to s. And this is kind of confusing because if you notice, these two are just the inverse of each other. So which one makes sense? Is temperature equal to equation 1 or is it equal to equation 2? Well, it turns out that both are correct in principle, but it makes intuitive sense that the second equation is better because as you're increasing temperature, energy increases. There's a more formal proof for this, but for now, it's just easier to understand that the second equation just makes more sense. So now we can rewrite temperature in terms of the partial derivative change of u with respect to s, which is simply the inverse of equation 1. And this should look pretty familiar because if you notice the thermodynamic definition of entropy is ds equals q reverse over t. And if you just switch these two, you get ds equals du over t. And it turns out that we can use this proof as a way to show that this is always true. Because if you notice here, it says Q reverse in a reversible process, but it turns out that it's always true. So how can we prove this? Well, recall the first law of thermodynamics, that the total change in energy equals the change in heat and the change in work. So we can rewrite dq, as Pujan talked about, as the partial derivative change of u with respect to s, because if you notice here, dq is simply t times delta s, and then the work is simply the external pressure times the change in volume. If you recall the piston example of when you're expanding the piston, the work is change of volume times the external pressure. So now we have du equals the temperature times the change in entropy minus pressure times the change in volume. If you rewrite this, move this to the other side, we get this du plus p times dv. And all these properties are in terms of the system. And if you rewrite this, we notice that all this is essentially restating the first law. So we can just cross everything out, and this becomes dq reverse. And if you rewrite everything, we get back the this thermodynamic definition of entropy. So what was the point of all that? Well, this all goes back to we want to rewrite entropy in terms of energy, and that's how we get back to the Gibbs-free energy. So now we have the second law, and we want to rewrite everything in terms of energy and in terms of heat, and focus on the system, not the surrounding. So this first term is fine, but we want to rewrite this in terms of the system. So we know that we just proved that ds equals dq over 2 t. So we can rewrite the change in entropy of the surrounding in terms of the change in heat of the surrounding with respect to t. And since whatever heat is released from the surrounding goes into the system, or vice versa, we can just write the negative change in heat of the system over T equals the ds surrounding. So if we plug this into the second law of thermodynamics, we get we can just plug this in here, and also we have to introduce another term, enthalpy, which is simply the change of heat at constant pressure. And since everything in the body we're assuming is happening at constant pressure, we can rewrite this negative dq cis over T in terms of enthalpy, and we get negative the dH cis over T. And we just put everything back into the second law, and we get this final equation, which should look pretty familiar, because essentially we're just rewriting this dH cis minus temperature times the change in entropy, and we're introducing a new variable called the Gibbs-free energy G, and which is the enthalpy minus temperature times temperature times the entropy. So what is this Gibbs-free energy? It's showing how spontaneous change occurs in the direction of reducing Gibbs-free energy. And just as entropy is maximal when increasing it, Gibbs-free is maximal when reducing it. So at equilibrium, entropy is max. At equilibrium, Gibbs-free energy is 0. And if you look at the equation, it depends on enthalpy and entropy. So reducing enthalpy is favorable, and increasing entropy is favorable. And also another thing I like to point out is that entropy is more prevalent at higher temperatures, because at higher temperatures, this gets higher. So essentially, the higher the temperature goes, and you can think of it as entropy is more powerful in determining what Gibbs-free energy is. And moving forward in the class, we'll use this equation to understand things like reduction potentials and kinetics and enzymes. So it's a very important term moving forward. And that's all I have.
Great. Okay, so I will stop